Hello everybody. So in this last main part of my talk, we will concentrate again on very complex tasks which we will model using our neural speech production and speech perception model, which we developed in the NENGO framework. So, and it is picture naming again, but in this case, we include a disorder. So the model has problems with lexical access. So in most cases, in this picture naming task, the model feels to have the word on the tip of the tongue, but has problems to find the correct lexeme and to produce it. How can we overcome this problem? So we can overcome this problem by introducing phonological or semantic cues. So if the model is not able to produce the word, we can add a phonological or a semantic cue and increase the performance. So what does it mean? Picture naming with phonological or semantic cues. So in the case that the word is on the tip of my tongue, so the patient has problems in lexical access or in lexical retrieval. In this case we use cues, but first of all I would like to tell you we adjusted the model in the way that this case of neural dysfunction leads to correct productions only in 20 to 45% of all cases, and in other cases we need the cues. So what is a semantic cue? For example, if the target word, so the word which is visually presented is car, the cue may be that we add or help the patient by saying, you can drive it, or look, it has 4 wheels. I'm sorry, four. And in the case of phonological cues, the help is, for example, for the word car. So please think on a word which starts with K. So first of all, let us concentrate again, how can we introduce this neural dysfunction? We introduce it by weakening a associative memory, which is represented by this arrow. It is the associative memory which activates the lexical items if a concept is already activated. And that is the tip on my tongue phenomena. I know what I want to say, but I can't find the correct word. So that is why this neural association is weakened. So the lexical form cannot be found, or an incorrect lexical form is found, and this incorrect form is produced, or if we have no activation here, no word is produced. So how do the cues work if a word is not produced or not produced correctly? So first of all, in the case of semantic cue, it leads to an increase of the neural activity in the concept level of the perception side. So we have the visual cue is coming in here. We have some activation here, and now yes, and this activation does not lead to a production. And in this case, we get an auditory input. So in the case of the car, maybe the additional semantic cue is, okay, it is an object with 4 wheels, or you can drive it. So, and then we get this information as well here and hope that it leads to an activation, to increase in activation here. In the case of a phonological cue, it works in the same way, an increase in neural activation on the perception side. So that means we get an increase here. So we have the word car to say. So we try to activate all words or syllables starting with K. and hope that we get a co-activation of the word car here that increases the strength of the activation here. But the shortcoming of both pathways here, that we always use the lexical pathways and always come to this point where we always have the problem to find the correct word, but the help may lead to a situation that the concept activation here now is stronger, so that may overcome the problems in this neural association and this neural connections, and that this stronger activation here may lead to a correct activation here at the lemma level. But at least for the phonological cue, we could imagine another pathway. We have this shortcut pathway from here to here. So if it is the case that we have a weak activation of the correct word and a weak activation of the correct phonological form, but this activation is not able to activate the motor item, so that could be, this shortcut could be helpful in order to to find the correct word at this level. And indeed, here we see the results of our simulations. So we have two different cues, the phonological and the semantic cue, and we have two different models. The first model we are looking is without the shortcut, and the second model is with the shortcut added. Sorry, here's something wrong. From the perception to the production side. And yet, in case of both models and in case of both cues, we get an increase in correct namings, so it increases the performance of the picture naming task. And due to this lexical access problem, we have a starting rate of correct words which is just about 24 to 45%. So the explicit results are given here. This model is is the complete model without shortcut. Here with shortcut, here again without shortcut, and here we see the results for phonological cues, here as well for phonological cues, and here for semantic cues. And what we see, if the shortcut is added, we indeed get the highest increase rate in producing correct words. So this is the word rate, the correct number of target word activation before a cue needs to help. So this is the rate of already correct generated words, and we do not need any cue. This is the increase of words if cues are coming into to help, and this is the resulting value of correct spoken words. So what we see is that in the case of the added shortcut, we have the strongest increase in correct word production for the phonological cues. And whether we take phonological cues or semantic cues, in the case that we only use the lexical route and not the shortcut, the result is more or less about the same. So what we would like to study now are four cases, are the activation plots again in for four simulation cases. We start with the phonological cue, that are the first two cases, and the target words are the words snake and apple. In the second case, we have in addition the shortcut. For snake, we have no shortcut, just the lexical route. And then we, in the last two examples, we have a semantic cues and try to produce the words duck and fly. In all cases, the words are not produced without cues. Yeah, and in the fourth case for fly, we see a rare case. Here first a different word is activated. So why the lexical access problem in the case of the first three cases leads to no production. In the fourth case, it leads to the production of the wrong word. The word flee is activated, while fly should be activated. So we look at the first point, phonological cue, in order to get the correct naming for the picture naming task snake. So we see at the control level, it starts with in the same way as our other picture naming tasks are starting. So we have a priming for 100 milliseconds, look and think, and then we now have a longer interval for letting the model try to find the correct word. For 600 milliseconds, we have the control activity, try to utter the noun. And then later we see here there comes two further control activities, which mean listen to a cue and try to utter the noun. So here the cues come in two times, here for the first time and here for the second time. So the cues come in when I go to the bottom at about 700 to 800 milliseconds. And a second time at about 1 second and 500 milliseconds. Okay, so here the control output is try to produce the noun just from the visual input, and here try to produce the sound, the noun with from the visual input, and in addition you now get a phonological cue. So the visual input, okay, the visual input is only given for the first 800 milliseconds. And what we see, if we go down to the results, is that we have no motor activations. So we really need the cues. And here the cues come in, the phonological cue. I will go down again. So the perception, on the perception level, we get the input of the syllable snare. So it means the word starts with the syllable snare. And what we directly see here on the perceptual level, because we have S-pointer networks, we already get an increase here of all words on the phonological side starting with snare, and one of these words is snake as well. Going up to the lemma level on the perception side, we directly see that due to the cues, we have a strong activation of the word snake, and as well snake, snail, and other words are activated here on the perception level. What we see here on the production side is then we have already a correct production main activity of the word snake from the visual input, but we see if we go to the lemma level, the activity of the lemma for snake is in concurrence with the activity for the word for another word here, and the word is not activated. It's I do not see it. It seems it is the word snail. The word snail, which is co-activated here, which leads to problems at the phonological level, and we have no activation. So now, if the phonological cue is given, we get a slight higher activation at the production level, which then, at least here, leads to slight higher activations and to deactivation or to a lower activation of a second word, which here had the same level, which is in concurrence with this correct word. And we see that opens a chance here, this difference here in activations opens a chance to produce just one correct word, and that is then activated here for short moments on the production side, and then leads to a correct activation at the motor level. So and sometimes, and this is typically again for the neural character of the whole model, for this character introduced by spikes and by a statistical behavior, and we have some noisy signals. So here we have just a very small increase in activity, and this increase in activity seems to form a starting point, an initial point for a longer activity of the correct word on the phonological level, and that leads gives an impulse for the for the starting of the activation of the correct word or the correct syllable on the motor level, on the syllable plan level. So we look at the second word. So the visual input now is apple, and it's again a phonological cue, which is given in app is the cue. And what we see here from the cue is the same thing again. The word apple is directly, strongly activated, but what we see here from the lexical level, it does not help. So we have already from visual input a strong activity of the concept apple on the production side, and it is not increased here by the perceptual level, but we see it is increased because of the shortcut. We have an activation here already on the phonological level for the correct word, but it is not sufficient for activating the correct motor plan. We see it tries to start, some activity starts here, but it is not enough for activating the syllable. And we get a stronger activation of the correct phonological form as a result of this perception production short pass on the phonological level. So here the word activation is increased because as a byproduct to the activation of the syllable app, because of the similarity, all the words starting with app, like apple or apricot or apice, are co-activated, and these words, and so the activity of the word apple is now the strongest here and starts the activation at the motor level. So the next example is a semantic cue. So the input word is duck, and we give a semantic cue. So the input is a duck is a bird. And what we see here, and we again see, looking at the production level, the production activity here on the production pass for the word duck, which is correctly identified from the visual input, but it is just on the tongue of the model, and it can't be produced. At least the lexical form is produced, but it is too weak to produce a strong phonological form. So again, the correct phonological form is produced here as well, is activated here as well, but is not strong enough to activate the correct syllable form. So it is on the tip of the tongue, the word, but it can't be produced here. What helps are the semantic cues, which, the word bird is here activated, but on the perception level, we get a co-activation or stronger activation than of the word duck, which is co-activated, which is semantically, which is similar with the word bird. So, and that leads to a stronger activation of the word duck here, at least on the phonological level, and that leads to a stronger production than here, or let's say the production starts because we have the semantic help, the semantic cues. So last but not least, the fourth case is a rare case. It's a very complex case. I already told you it should be the word fly, which is on the picture for the picture naming task, but the word flea is produced. And here we will see it will be corrected later on because the semantic cue is blue bottle, and blue bottle or meat fly is semantically near to fly and not thus near to flee. So to be very short, so here we have the word fly, which is activated visually, and the word fly is co-activated here on the production level, but we see here on the lemma level, again, because of the problem that we have this lexical access problem, a second word is co-activated. That is the word flee. Both words are activated to the same degree. And in this case, it's typical to the statistical behavior of the model. One of the models is activated. And here it's not the word fly, it's the word flee. It could be the word fly, and then we would have a directly correct activation, and we do not need the semantic cues. But here, the wrong word is activated. And because the word blue bottle is activated, this leads at least we cannot see really what's going on here on the perception level. It is always like in the example before, the semantic cue which is activated then to a higher degree, but at least it leads on the lexical level to a decrease of the incorrect word. And so now we would have a chance to get a stronger activation for the word fly on the phonological level, which directly occurs here. And indeed, that leads to the fact that later on, after 1.7 seconds, the word fly becomes the highest degree activation, and that could be lead to a behavior of the model that first the word flee is produced, and then we get a correction that the model says, okay, no, it was not flee, it is the word fly. So what we see is that due to this rare case, the model as well is capable of doing correction processes. So, coming to an end, what about the realism of the model? I think, especially to my discussion of these rare cases, and of course to all the other cases, we see that the model is realistic. Coming from the modeling side, from the architecture, it is clear that single neurons and connections are modeled realistically. For example, that for the single neuron model, we use a leaky integrated fire model. So we really model spiking, which is not done in all neural models. There are models that are just using a mean activity over time. Here we have real spiking modeling, and we are modeling the time domain in looking in time steps of milliseconds. We have seen that the corticocortical loop, the basal ganglia and thalamus loop, is modeled in detail for a really biological process control. And the concepts, the NENGO concepts for neuron buffer, memories, associative buffers, binding buffers, and S-pointer networks are developed to a very high degree, and we have seen that this leads to a good modeling of all types of behaviors which may occur in human data. So, the large-scale model we have introduced here approximates human behavior surprisingly well in many cases. We have seen it for the serial recall task, the results given by Xu, that we have the concave form for the performance result. The middle words have a lower production probability than the words of in the series in the beginning and the end of the series. Then remember the rare cases. Our neural model allows the modeling of rare cases, for example, for normal picture naming. That was my study from 2016, where we saw if we do 500 or 600 production simulations for one word, we find in, let's say, 3 to 6 productions we find a fail in production or an error, even if the model is not including any neural dysfunctions. And we have seen that cues are helpful. So in our case of lexical access problems, which may be a symptom of mild mixed aphasia, we have an increase in correct word naming from 20 to 55, or a maximum from 45 to 70%. Moreover, we have seen the modeling of symptoms for different types of aphasia. In an earlier talk, we have seen that this leads to a decrease in performance with an increase in strength of the disorder. Then in the video before this video, in the last videos, we saw that modeling picture naming with destructor words makes the task of picture naming more complex and leads to a decrease in performance in the case of occurrence of destructor words. So, in many cases, I think we get a good approximation of the human data on the qualitative level, but in some cases, the approximation of the human data on the quantitative level is still moderate. We saw that, we discussed that for the destructor, for the picture naming with semantic or phonological, similar or dissimilar destructor words. There are a lot of human data available, and we see that the model does not really approximate the human data quantitatively very well, while in the case of the serial recall task it does, but in this case it does not. So at least there is some space for increasing, of course, the model, but at least I would like to say that all types of human behaviors, all effects occurring in speech screening tasks can already be modeled qualitatively by using our speech processing model. What are the benefits from our model? So in medicine or in speech therapy research, we can use the model for the simulation of behavior of patients. We can simulate the speech screenings, and we can simulate neural dysfunctions, and we get results which are quite close to reality. Why can we create simulation patients? Yes, because we can introduce neural dysfunctions, and so we can specify or define the neural dysfunctions very clearly by using a model. So at least we can define a group of patients with the same neural dysfunction, with the same type of disorder, and with the same strengths of a disorder, and that allows to check different versions of a screening by using these patients, because they do not learn from one to the next screening. And we can vary screenings and look whether different versions of a screening lead to an increase in sensitivity for detecting a specific neural dysfunction, especially that what is introduced here in the group of patients checked here in the simulations. So, and that is a real benefit we could have from models. We cannot do that using real data, because we never get such a huge amount of patients with the same disorder, with the same severity of a disorder. And if we use them for tests, we cannot do the tests described here, because we have learning effects for these patients. So in this case, modeling could be very helpful to come to better screenings and to better therapy forms for patients suffering from specific speech disorders. Thank you so much.